At the core of every computer are devices that actually perform the computations. In most modern computers, we either use NMOS and PMOS transistors as the base of most of our operations, and in this lecture we'll be focusing on how we use these two transistors to create logic gates. Now, this is the NMOS transistor itself inside this circle, and we have some conventions of how we use it. So we connect this lower terminal, terminal 2, to ground. It's sufficient just so you know that this is the convention, and you can explore why in future courses. And then we have a gate, which is our inputs, and that's how we control the transistor from our perspective, and that'll be a 0 or a 1. And then this terminal 1 connects to other gates or the output of our logic gate. And then we've got our PMOS transistor over here, which behaves in an opposite fashion. We have our transistor here, and notice this little symbol that tells us this is the PMOS transistor. And we connect terminal 1 here to this high voltage VDD, which is usually like about 1 volt, but that's going to be varied based on the technology. And then we have our input gate, which allows us to control this transistor, and then terminal 2 connects out to other circuits or other logic gates. And so how do we actually make these work, and what do these actually do? And so basically a transistor is a electrically controlled switch. If we put a 1 in, or a high voltage, the NMOS becomes a closed circuit, whereas the PMOS becomes an open circuit. And if we were to switch, let's explore this a second longer. So when this is closed or shorted, there's a direct path from ground up to here. So basically our output terminal has a 0 volt output. Whereas this guy, since there's an open circuit, there's no current or anything going through this. And so this is just basically a dangling wire. There's nothing there. It's not connected to anything. However, if we switch our inputs, the entire behavior changes. Our NMOS becomes an open, and our PMOS becomes a short. And so now there's a direct path between our output and VDD. So now this is going to be our high voltage VDD. And we can keep altering these behaviors. We can alternate them between 0 and 1s. And because they have opposite functionality, we call them complementary. And complementary MOS or CMOS is how we talk about NMOS and PMOS as a group, and any other type of logic that has a similar functionality. The amazing thing is that we can use just a PMOS and an NMOS transistors to create any circuit. And so here we have a NOT gate, and we'll show you how this works. If we have an input of 0, our P-type is going to become a short and directly connect the output to VDD. So when our input is 0 volts, our output is going to have VDD volts, which is a logical 1. On the other hand, this N-type is going to be open, so there's no connection between our output and ground. If we input a 1, or VDD volts, we have a direct path between ground and the output, so our output is going to have 0 volts and be a logical 0. And our P-type is going to become an open, so there's no connection between VDD and the output. And so this is how we build our NOT gate, which has this symbol. When we build more complicated or complex digital logic circuits, it becomes important to notice there's another part of what makes these guys complementary. So down here, NMOS transistors are connected in series. That means the output of one is connected to the terminal of the other. Whereas our PMOS up here are connected in parallel, where both of their outputs are connected together, and they're both connected on their terminals to VDD. And these differing paths, this parallel path versus series path, is really important. That anytime you have a PMOS in parallel, you need to have an NMOS in series. If you have a PMOS in series, you need to have an NMOS in parallel. And that's how we build our logic gates, so that we maintain this complementary functionality. Now let's look at what this circuit actually does. So let's input A is 0, B is 0. So when A is 0, this PMOS is going to be a short, and when B is 0, this PMOS is going to be a short as well. And so both of these connect our output directly to VDD. So our output should be a 1. And down here, our A is connected to our NMOS, so that's going to become an open. And B is going to be connected to this NMOS and create an open. So there's no path between ground and the output. So indeed, our output is 1. And let's try another input combination. So let's try with 0, 1. And when A is 0, we're going to have a short on this PMOS, just like before. And with B is 1, this is going to create an open on this PMOS. A with 0 is going to create an open on this NMOS, and B with a 1 is going to create a short. So here, our ground is still cut off from the output, but we do have a direct path from VDD down to the output, so our output's going to be 1. Now let's try the next combination, 1, 0. This is going to be exactly like before, except a little bit flipped. So A is going to result in this being open. This B is going to cause this to be short. And then this A is going to cause this NMOS to be shorted. And this B with 0 is going to cause this NMOS to be open. So again, there's no path between ground and the output. But there will be a path between VDD and the output. So the output is 1. All right, one last combination to go. We got A is 1, B is 1. That means A is going to be an open on this PMOS, B is going to be an open on this PMOS, and then A is going to result in a short on this NMOS, and B is going to result in a short on this NMOS. So now we have a path between ground and the output. So our output is 0, and we have no paths between VDD and the output. So that reinforces that this is a 0. If you recognize this truth table, you should recognize that this is the NAND function, the not and, which has the following circuit symbol. We can now use this NAND gate that we constructed to create an AND gate if we just concatenate this not afterwards. So we've got our NAND, and this is our not, and this would result in A, B as our inputs, C as our outputs for an AND gate. And this is one reason why we tend to use only NAND gates in our implementation of actual computers, because an AND gate is a lot more complicated. Anyways, we'll find out more about that in future lectures as well. So let's look at one last circuit, and I'll just give the punchline away for this one. This is a NOR gate, and we'll see exactly how this behaves. But I want to draw attention back to the series versus parallel. Here, our PMOS are in series, whereas our NMOS down on the bottom here are in parallel because they share that common point over here. And so that should hopefully reinforce the idea that we always do things complementarily between PMOS and NMOS. So let's look at the inputs. When A is 0, B is 0. A creates a short on the PMOS, B creates a short on this PMOS, and then the A comes around here and creates an open on the NMOS, and B creates an open on this NMOS. So we have a direct connection between VDD and the output, and no path between ground and the output, so our output is 1. Let's try the next input combination with 0, 1. 0 creates a short here and an open here. So there's no path between VDD and the output. And then we've got 0 over here, so this guy becomes an open, but the B being 1 here creates a short for this NMOS, so we have a path directly from ground to the output, so that creates a 0 output. Next input combination, 1, 0, B is 1, so we have a open here and a short on this PMOS because of the B, And then this guy is going to be open, and this guy will be shorted. So now we have a different path, but we still have a path nonetheless from ground to the output. So our output will be 0. And then we put both of these as 1. Both of our PMOSs will be open, and both of our NMOSs will be shorted. So we have 2 paths from ground to the output. So C will be 0, and our output will be 0. And this, again, creates our NOR gate, which has the circuit symbol NOR. And we can combine NOR with NOT to create OR. And just like our NAND, we generally will prefer to use NOR gates exclusively in our designs rather than using AND, ORs, and NOTs.